Hello, welcome to my course on reinforcement learning. Today, I would like to make a short video to quickly introduce the contents of my course, and in the meantime, go through the key concepts and algorithms of reinforcement learning using such a diagram. This diagram outlines the 10 chapters in my book and the contents of my lecture videos. Each block in the diagram corresponds to a chapter in my book and a lecture in my course. Why am I making this video? In offline teaching, I used this diagram in the last lecture to help students review the contents learned over the entire semester. However, when transitioning this course online, I felt this video might be especially useful for those unfamiliar with my course, wondering whether it's worth studying my course. This video could help these students by serving as a comprehensive overview. In a short time, I will cover numerous concepts and algorithms, as well as analyze the relationships between them. It's unrealistic to master all these topics in such a short time, but hopefully you can grasp the basic idea and then formulate a learning plan based on your interests. Before diving into the details, I want to offer some advice on learning reinforcement learning, which I believe will be useful for beginners. First, it's essential to understand the goal of studying reinforcement learning, which encompasses two main aspects: fundamental principles and practical programming. This course focuses on the fundamental principles. If you wish to learn practical programming, there are many other excellent resources. If you are interested in understanding the principles behind many algorithms, this course is a good option. From my perspective, understanding principles is very important. Understanding the principles can provide a very clear comprehension of the algorithm you are using, its underlying principles, what it can do, its advantages and disadvantages, and where to start if you wish to innovate. These principles form a very important foundation. If you intend to study these principles, it is also essential to devise a plan that suits your current interests. Some may wish to systematically study all principles thoroughly, while others may focus on some specific topics. After setting your goals, it is important to allocate appropriate time for learning. How much time should you spend on learning the fundamental principles of reinforcement learning? Here, I am referring only to principles. For programming and practical application, you will need to invest additional time. First, I hope the readers can abandon the idea of quick mastery. For instance, expecting to grasp the basics in 1 hour or to become an expert in 1 day is unrealistic. In fact, the anxiety in our study and research often comes from not allocating appropriate time for a goal. For instance, planning to fully understand a paper in 1 day when a week is required can lead to frustration. Anyway, it's crucial to allocate appropriate time to your learning goals. Why do I encourage abandoning the idea of quick mastery? It's because the principles of reinforcement learning are characterized by two significant aspects: mathematical and systematic. If we wish to deeply understand some algorithms, intuitively explaining what an algorithm does will not suffice. Your understanding may remain superficial. However, once you grasp the mathematics behind it, what the math equation is actually doing, you will find that you can explain the algorithm comprehensively without any blind spots. The other aspect is its systematic nature. Later chapters build upon earlier ones. Jumping straight into advanced topics like Q-learning or policy gradient without a solid understanding of basic concepts only leads to a superficial understanding. So, how much time should one devote to mastering the fundamentals of reinforcement learning? Does it require an exceedingly long time? Not necessarily. For instance, this course totals approximately 11 hours, which will round down to 10 for simplicity. If you encounter difficulties halfway through, I recommend taking the time to understand them fully before proceeding. Suppose this approach will double the time to 20 hours, and if you need to study related basic knowledge, the time could double again to 40 hours. Is 40 hours a lot for learning reinforcement learning? If these 40 hours are spent efficiently and your foundation is strong, your understanding of reinforcement learning principles will be profound. Adding some practical experience, you'll be able to read papers without significant obstacles, making this time investment worthwhile. So, is 40 hours a long time? Think about it. In fact, it only takes 2 weeks, excluding weekends. That's 10 days in total, with 4 hours each day, split into 2 hours in the morning and 2 in the afternoon. This schedule still leaves you time for other activities. Overall, spending some time to make solid progress might seem like the slowest approach, but it is actually the most efficient way in the long run. Now let's take a closer look at this diagram, which is not only featured in my course and book, but also serves as a structure for the principles of reinforcement learning. The diagram is divided into two main sections: fundamental tools and algorithms. The fundamental tools include basic concepts, Bellman equation, and Bellman optimality equation. The algorithm section include value iteration and policy iteration, Monte Carlo learning, temporal difference learning, and value function approximation, policy gradient methods, and actor-critic methods. Each part of this diagram is important, but their importance varies in different aspects. The importance of the chapters at the beginning primarily lies in their foundational nature. The concepts and ideas introduced in these chapters form the basis for the subsequent ones. The chapters toward the end highlight more advanced and practical aspects of reinforcement learning. Now, let's begin the detailed introduction. I will discuss each chapter in two main aspects. First, the content covered in that chapter. Second, its relationship with preceding and succeeding chapters. I'll go through some topics very quickly. As mentioned, this is just an overview. The purpose is to let you know the basic framework. It's totally okay if there are many topics you don't fully understand. If you're interested, you can delve deeper into those topics later. The first chapter introduces basic concepts such as state, action, reward, return, episode, and policy. These concepts are crucial for understanding reinforcement learning and are widely used throughout the course. A grid world example involving a robot searching for a target area is used to illustrate these concepts intuitively. These ideas are then formally framed within the context of a Markov decision process, which is called MDP. Overall, the basic concepts introduced in the first chapter are fundamental and widely used in reinforcement learning. The second chapter focuses on the Bellman equation. This chapter contains two crucial points. The first is a concept, and the second is a tool. Once you understand this concept and tool, as well as the relationship between them, the chapter will become very clear. What is this concept? State value. What is a state value? It is the average of the rewards obtained by starting from a certain state and following a specific policy. A higher state value indicates a better policy, as it means more rewards are collected from that state following the policy. Conversely, a lower state value suggests that the policy yields fewer rewards from that state, indicating a less effective policy. Why do we focus on state value? Because it allows us to evaluate whether a policy is good or bad. Given the importance of state value, how do we analyze it? This involves a tool. What tool? Bellman equation. The Bellman equation, in a nutshell, describes the relationship between the values of all states. What kind of relationship is this? It is actually an equality, an equation. I will not introduce the specific symbols here. By solving such an equation, we can determine the state value of a given policy. Thus, I can evaluate whether the policy is good or bad. Solving the Bellman equation to obtain the state value of a policy is a process known as policy evaluation. Policy evaluation is a fundamental concept in reinforcement learning. Once I have evaluated a policy and obtained its value, I can then improve upon this policy and continue this cycle. Ultimately, we can obtain an optimal policy. Therefore, this concept is very important. We now approach Chapter 3, the Bellman optimality equation. As suggested by its name, the Bellman optimality equation is a specific case of the Bellman equation. While each Bellman equation corresponding to a particular policy, the Bellman optimality equation, being a special instance, is also associated with a policy, the optimal policy. Why do we focus on the Bellman optimality equation? It is because it describes the optimal policy. This is related to a fundamental question: what is the ultimate goal of reinforcement learning? As I have told my students, upon encountering this question, you must quickly respond that the ultimate goal of reinforcement learning is to find out the optimal policy. Therefore, Chapter 3 is of significant importance. To study Chapter 3, we need to grasp two main points. The first key point is two concepts: the optimal policy and the optimal state value. A policy is defined as optimal if it yields the highest state values, higher than those obtained by all other policies. This concept is crucial. How do we analyze this crucial concept? Here, the second key point comes into play, a tool, which is the Bellman optimality equation. Its expression is quite simple. Here it is presented in matrix vector form. For those encountering it for the first time, I believe you need spend some time to understand it, but it will be well worth the effort. This equation offers profound and comprehensive insights. A significant portion of that chapter is dedicated to explaining the Bellman optimality equation. When analyzing the equation, we utilize the fixed point theorem. This fixed point theorem reveals two significant properties of the equation. The first aspect addresses fundamental problems. For example, do the optimal policy and the optimal state value actually exist? The answer is yes. Their existence is a basic premise. Without it, there would be no point in pursuing them. While the optimal policy may not be unique, the optimal state value is unique. An optimal policy could be deterministic or stochastic, but there always exists deterministic optimal policies. The second aspect is that it provides us with an algorithm solving the Bellman optimality equation. By solving this equation, we naturally obtain the optimal policy and the optimal state value, thus achieving the goal of reinforcement learning. Therefore, Chapter 3 is critically important. Its importance lies in the definition of optimality, as it directly links to the ultimate goal of reinforcement learning. With this, we have completed the introduction to the first three chapters. We now move on to Chapter 4, which introduces value iteration and policy iteration. This marks the beginning of the section on algorithms and methods in this course. By studying this chapter, we will understand what the first set of algorithms capable of solving for the optimal policy are. Specifically, we will learn three algorithms here. The first is called value iteration, the second is policy iteration, and the third is truncated policy iteration. What is the relationship between them? Truncated policy iteration is a unified algorithm of the other two, or it could be said that value iteration and policy iteration are two extremes of the third. For specific details, you can check this chapter more closely. What I want to emphasize here is the value iteration. Recall when I mentioned an algorithm capable of solving the Bellman optimality equation in Chapter 3. That algorithm is actually the value iteration algorithm. We will analyze it more details in this chapter. Furthermore, in the following chapter, Chapter 5, policy iteration, will have a significant foundation for the Monte Carlo learning that do not require a model. What common characteristic do these three algorithms share? They are iterative algorithms, and each iteration consists of two substeps: policy update and value update. What does this mean? It means that at the current moment, if I have a policy that is not very good, it's okay. I estimate the value of this policy, which is essentially conducting a policy evaluation. After obtaining the value, I use this value to improve the policy. Once the policy is improved and a new policy is obtained, I estimate its value and then improve the policy again. Thus, there are policy update and value update steps that continuously iterate until I find the optimal policy. This concept is not limited to Chapter 4. All subsequent algorithms in reinforcement learning operate on this principle. They continuously iterate between values and policies. The form of the algorithms may differ, but the underlying idea is similar. Additionally, the algorithms introduced in this chapter require a model. What is a model? You can check the book for an explanation. If we do not have a model, what should we do? We can proceed to Chapter 5. Chapter 5 introduces Monte Carlo learning, which is the simplest reinforcement learning method that does not require a model to find optimal policies. Transitioning from Chapter 4 to Chapter 5 presents a significant gap, since it's the first time we face a situation without a model. What should we do when we lack a model? Sometimes this can be confusing. In fact, 2 points need to be clarified. First, when you do not have a model, what do you aim to do? Second, without a model, what do you have? What do we aim to do? The answer is that we aim to estimate the expectation of some random variables. Why is this important? It's because, as we've previously mentioned, concepts such as state value and action value are all expectations of random variables. On the other hand, what do we have? We have random sampling data. For example, suppose there is a random variable x, and its samples, let's say xi. Having many such samples allows us to calculate an average value, denoted as x bar, which serves as a good approximation of ex. Therefore, without a model, you need data. Without data, you need a model. Without either, we can do nothing. By applying this idea to reinforcement learning, we obtain the first reinforcement learning algorithm that does not require a model. Specifically, we introduce three algorithms: MC Basic, MC Exploring Starts, and MC Epsilon Greedy. The complexity of these three algorithms increases sequentially. The first one, MC Basic, is very simple. What is it exactly? It's essentially the policy iteration algorithm introduced in Chapter 4, but I've removed the part that relies on a model and replaced it with a part depending on data. However, this MC Basic algorithm is not practical due to its low efficiency. Then, why do we still need to study it? It's because I want to separate the complex aspects from the core essence, showing that the most fundamental ideas are actually very simple. The reason for the complexity introduced in the latter two algorithms is to enhance efficiency to better utilize data and other improvements. At this point, you may have realized that reinforcement learning is truly systematic. Many parts depend on each other. For instance, to study Monte Carlo learning, we must first understand policy iteration. To understand policy iteration, understanding value iteration is prerequisite. To understand value iteration, we must first study the Bellman optimality equation. To study this, you must first study this, and to study this, you must first understand this. Thus, beginning your learning from any middle point, without a solid foundation in the preceding concepts, might lead to a superficial understanding. Now let's proceed from Chapter 5 to Chapter 7. In Chapter 7, we will introduce temporal difference learning. However, before we delve into that, we first need to discuss Chapter 6 on stochastic approximation. Why is this necessary? It's because there is a significant gap between Chapters 5 and 7. Specifically, the algorithms in Chapter 5 are non-incremental, whereas in Chapter 7 they become incremental. For beginners, encountering these algorithms for the first time can be confusing. Questions about why the algorithms are designed this way in the first place and what problems they aim to solve may arise. Therefore, we'll press the pause button here to lay a solid foundation before moving forward. The first problem we address here is mean estimation, essentially estimating the expectation of a random variable. Why do we do this? We aim to illustrate the difference between non-incremental and incremental methods. To estimate EX, there are two approaches. Non-incremental method involves, for example, collecting 10,000 samples and waiting until all samples are gathered to calculate the average all at once, providing an approximation of EX. On the other hand, the incremental method starts with an initial estimate, which may not be accurate, but that's okay. With each new sample obtained, this estimate is updated. Each new sample refines the estimate, gradually increasing its accuracy. This method represents an incremental algorithm, offering the advantage of not having to wait to collect all 10,000 samples before utilizing the data. As samples are collected, they can be immediately used. Specifically, in this chapter, we introduce three algorithms. The first is the Robbins-Monroe algorithm, abbreviated as the RM algorithm. It essentially addresses the problem of solving this equation where a simple function equals 0. G is the function and W is the variable. The question it answers is, at what value of the variable W does the equation GW equals 0 hold true? Interestingly, the RM algorithm does not require knowledge of the function GW, its expression, or its gradient to find a solution. The second algorithm is the very useful stochastic gradient descent, SGD, which has widespread applications not only in reinforcement learning but also across various other fields of machine learning. We provide an extensive analysis of SGD and also point out that it is a special case of the RM algorithm. Additionally, we compare SGD with batch gradient descent and mini-batch gradient descent. Overall, Chapter 6 lays the foundation for us. It focuses on two key points. First, the manner of incremental algorithms, and second, the stochastic gradient descent algorithm and its ideas, which will have widespread application in subsequent chapters. With the knowledge introduced in Chapter 6, moving on to Chapter 7 becomes easier. Chapter 7 focuses on temporal difference learning, a very classic algorithm in reinforcement learning. Specifically, we introduce several algorithms. First, we introduce how to use TD learning to learn state values. The task of learning state values, which has been introduced in previous chapters, is revisited here. For instance, the Monte Carlo learning can be utilized to learn the state value, and value iteration and policy iteration can also learn the state value based on models. Here we employ the temporal difference learning to compute the state value. Therefore, while they are all aimed at similar objectives, the methodologies differ. This algorithm is further extended to SARSA, which applies TD principles to learn action values. Once the action value is determined, it can be used to update the policy, leading to the development of a new policy. This loop of evaluating action values and updating policies continues, enabling continuous improvement until the optimal policy is obtained. The third algorithm is the well-known Q-learning algorithm. A unique feature of Q-learning is its direct computation of the optimal action value, making it an off-policy algorithm. This involves the crucial concepts of on-policy and off-policy in reinforcement learning. What do these two concepts mean? In reinforcement learning, there are two policies: the behavior policy, which is utilized for generating experience data, and the target policy, our goal policy, that we aim to continually refine in hopes of converging to the optimal policy. If the behavior policy and the target policy are identical, the approach is called on-policy. Conversely, if they are different, the algorithm is called off-policy. The advantage of off-policy methods is significant. They allow us to leverage data generated from other policies. We can use this data to learn optimal policies. Towards the end of this chapter, a unified point of view of the algorithms introduced in this chapter is provided. We introduce numerous algorithms whose expressions are remarkably similar. The mathematical problems they solve are also similar. Now we move from Chapter 7 to Chapter 8 on value function approximation, where a significant gap exists. What is this gap? Until Chapter 7, all state values were represented in a tabular form. For example, the state value v pi s, where s is a state, and each state corresponds to a state value. These state values are stored in a table or vector, making access or modification quite straightforward. However, the issue arises when there are a vast number of states, or the states are continuous. In such cases, the tabular form becomes inefficient or inapplicable. Therefore, we turn to function representation. At this point, I use v hat, where v remains the value, and the hat symbolizes approximation. Then SW, where W is the parameter corresponding to this function. We hope this function can approximate the true v pi s as closely as possible. Specifically, the first algorithm introduced here employs the value function approximation for state value estimation. This was actually mentioned just now. Different chapters introduce different algorithms for estimating state values. How is this done here? The method is quite straightforward, involving 3 steps. First, we define an objective function. Second, we calculate the gradient of this objective function. Third, we use gradient ascent or descent to optimize this objective function. Specifically, the objective function JW represents the average difference between the actual state value v pi s and the approximate function value v hat. The goal is to find an optimal W that allows this function to accurately approximate v pi s. This concept can also be integrated with SARSA and Q-learning. By estimating the action value and subsequently combining it with policy improvement, we can iteratively refine our policy to find the optimal policy. An important part to highlight is the introduction of deep Q-learning, or DQN. Various techniques within DQN, such as using 2 networks or experience replay, are discussed in detail. Overall, Chapter 8 marks the beginning of a new chapter, where we introduce the concept of functions. Neural networks serve as an excellent representation of functions. Hence, in Chapter 8, neural networks come into the field of reinforcement learning for the first time. Now, as we move from Chapter 8 to Chapter 9, we encounter another significant gap. What is it? Up to Chapter 8, the methods discussed are all value-based. Starting from Chapter 9, we study policy-based methods. What's their difference? Let me give a simple example. Recall from Chapter 8, we discussed a target function JW, where W represents the parameters of the value function. The goal was to update the value function's parameters so that it could accurately approximate or estimate the values corresponding to a policy. Upon this foundation, we can update the policy, evaluate its values, and iteratively refine the policy to find the optimal one. Policy gradient methods, however, differ slightly. Here, the target function is J theta, where theta denotes the policy's parameters. We transition from representing policies in tabular form to function form, allowing us to directly optimize theta and consequently modify the policy directly. This is the intuitive difference between the two approaches. In Chapter 9, we focus on the policy gradient method. Its fundamental idea is straightforward. First, identify the objective function. Second, calculate the gradient of this objective function. Third, use gradient ascent or descent to optimize the objective function. This methodology is extensively applied in reinforcement learning. For policy gradient, there are two types of objective functions discussed here, which interested readers can explore further. The gradient corresponding to these objective functions is known as the policy gradient. There is a well-known policy gradient theorem, which can directly give the expression of the gradient. Deriving this gradient is quite complex, but for most students it is sufficient to know its expression. Upon obtaining the gradient, we can proceed with gradient ascent, aiming to maximize the objective function. At this point, we introduce an algorithm named reinforce, a classic algorithm of policy gradient. Moving from Chapter 9 to Chapter 10 on actor critic, we encounter another gap, though it's relatively minor. Actor critic essentially merges policy-based and value-based methods by integrating the content of Chapters 9 and 8. In fact, the actor critic method is the policy gradient method introduced in Chapter 9. The term actor critic is chosen to emphasize the role of value, where the actor is responsible for policy updates, and the critic assesses whether a policy is good or bad by evaluating its value. How can we understand the actor-critic architecture? There are many intuitive explanations, but my favorite is to use a specific mathematical equation for clarification. It's not necessary to grasp the details of this equation in this video. What's important is knowing that this equation updates theta at time t to theta at time t plus 1, where theta represents the policy's parameters. Therefore, through this equation, the policy gradually improves, which corresponds to the actor component. During the update process, what is needed? The value q. To update the policy, this value must be calculated. Once obtained, it can be used to update the policy. This loop illustrates the interactive relationship between policy and value. Specifically, we introduce several algorithms in this chapter, including the simplest actor-critic algorithm, known as QAC, which is actually this equation. Another algorithm is the advantage actor-critic, abbreviated as A2C. There are two letter A's here, which introduces a baseline to reduce the estimation variance. The third one, since the actor-critic method is a policy gradient method, it is on policy. Can it be transformed into an off-policy method? The answer is yes. We can employ a technique called importance sampling. Importance sampling is not limited to actor-critic methods. In fact, all on-policy methods previously discussed can be converted to off-policy methods using importance sampling. Additionally, the policies mentioned earlier are stochastic, meaning there is a probability of selecting any action in every state. By contrast, deterministic policies can also be utilized, leading to the introduction of deterministic actor-critic methods. Through this rapid overview, I have covered the key concepts and algorithms in the reinforcement learning. While many details may not be fully understood, that is okay, as long as you grasp the general framework and can subsequently tailor a studying plan for yourself. This video will be successful. Before concluding, I would like to elaborate further on a particular point. Is this course suitable for you? Let me outline the features of this course, allowing you to make an informed decision. First, this course focuses on the principles rather than on programming practices. For those interested in learning programming, there are many other excellent resources available. Moreover, this course prefers to tell the story from a mathematical perspective rather than through intuitive descriptions. This approach is adopted because I believe it is the most efficient method of teaching. It allows you to understand the fundamental mathematical principles behind a problem. This course is particularly designed for students who wish to gain a deeper understanding of the principles of reinforcement learning, such as those planning to conduct research or innovate in the future. A profound understanding of the principles is essential for these purposes. Or, if your career is about reinforcement learning, securing a firm grasp on these principles is crucial. If you're looking for a shallow and intuitive understanding, you might find that the depth of this course exceeds your expectations. Some may be afraid that the mathematics and depth makes this course difficult to study. In fact, that is not the case. Approaching from a mathematical perspective, I believe, is the most efficient way to learn. Also, the mathematical concepts will be introduced gradually, with step-by-step guidance. Numerous examples will be provided to help build intuitive understanding. After this course, what should you study next? Practice, combining theory with practice, and then you can start reading papers, and you will not encounter big obstacles. You can explore and delve into many fascinating areas, finding your niche. That concludes the content of today's video. I hope it is helpful to you. Goodbye.